Hello everyone, I'm Liang from ETH Zurich. Today I'm happy to present our work on DPZero, private fine-tuning of language models without backpropagation. This is a joint work with my great collaborators, Bintong from ETH, Kiran from Amazon, Siwang from UW, and Niao from ETH. As the size of language models continues to grow, the memory requirement of backpropagation for gradient-based first-order methods is becoming a bottleneck. For example, if we want to fine-tune a 66 billion size OPT using ADAM-W, 16 A100 POs each with 80 gigabytes of memory are required. However, as demonstrated in the first work method, if we use zeroth-order method to avoid backpropagation, only 2 A100 are enough. Another concern is that high-quality fine-tuning data are often private, since language models tend to memorize and review sensitive information in the data. This leads to the need of starting off private fine-tuning. Differential privacy is the most widely accepted framework in private machine learning. We call an algorithm to be delta DP if its outputs onto datasets that only differ in one entry are close up to epsilon with probability at least 1 minus delta. This motivates the study of private and zeroth-order methods for memory-efficient fine-tuning of language models. In this work, we focus on the optimization problem with loss fs, which is an empirical average of per-sample losses on a dataset of size n. In theory, the convergence rates of both private first-order methods and non-private zeroth-order methods depend on the dimension d. However, they both perform well on fine-tuning billion-sized language models. For non-private zeroth-order optimization, a popular method is based on this two-point gradient estimator. Here, U is some random direction, and we estimate the gradient using its finite difference, which only requires two function evaluations. In theory, the convergence rate is d over t, where t is the total number of iterations and d is the dimension. This is d times worse compared to the 1 over t rate of first-order methods gradient descent. However, in practice, there is no significant difference between the performance of zeroth-order method MESO and first-order methods FP. In private first-order optimization, a well-known algorithm is DPZero. Compared to gradient descent, there are two modifications. First, we need to do per-sample gradient clipping that ensures bounded sensitivity. Second, a noise tailored to the sensitivity C over N is added to ensure privacy. When Z is sampled from this Gaussian, DPGD is epsilon delta dp and achieves a rate of root d over n, which depends on the dimension d. However, in practice, the performance drop due to added noise is even smaller on larger models. On a model of 300 million parameters, the drop due to privacy is 5.1, but the drop is 4.3 on a larger 1.5 billion sized model. This gap between theory and practice suggests that there might be some low-dimensional structure in language model fine-tuning. For example, as demonstrated in this previous work, the eigenspectrum of gradients decay pretty fast. This motivates our assumption of low effective rank, where we assume the Hessian is upper bounded by some matrix H, whose trace is bounded by R. We then ask the question whether we can develop a dimension-independent private zeroth-order method under this low effective rank assumption. A straightforward private zeroth-order method is to replace gradients in DPGD by their zeroth-order gradient estimators. However, this method still depends on the dimension even with this low effective rank assumption. The main bottleneck is that we have to choose a clipping threshold in the size of the upper bound of this estimator, which already scales with the dimension d. There are two observations behind the design of DPZero that achieves dimension-independent rates. First, note that the random direction U is a public information and there is no need to add noise to it for privacy. It is enough to clip the finite difference and add a scalar noise to ensure differential privacy. Second, although the size of this finite difference scales with d in the worst case, this only happens with low probability. With high probability, this size is nearly dimension independent, and we can choose C nearly independent of the D. As a result, under the low effective rank assumption, the convergence rate of DP0 is nearly dimension independent. Here is a summary of the algorithm DP0 and a comparison of convergence rates among different methods. We first test the performance on a synthetic quadratic example where we can control the effective rank. When the rank is D, every method scale with the dimension, and the straightforward method DPZero has the worst performance. When the rank improves to log D, DP0 becomes nearly dimension independent. We evaluated the performance on privately fine-tuning RoBERTa of 300 million parameters. The performance drop due to privacy is smaller for DP0. For example, when epsilon equals 6, the drop of DP0 is at most 2.6%, but the drop of first-order methods is up to 9.5%. The main benefit of DP0 is memory efficiency. Compared to first-order methods, there is nearly no additional overhead to ensure privacy. This is due to the novel design of per-sample loss clipping in DP0 that saves the overhead of per-sample gradient clipping in first-order methods. We also conduct experiments on privately fine-tuning OPT. Note that first-order methods already run out of memory on OPT 1.3b on our device, but zeroth-order methods can fine-tune models up to 6.7 billion parameters. Again, the performance drop is small for DP0. For example, the drop due to privacy is only up to 0.9% when epsilon equals to 6. That's all. Thanks for your attention.